Again, another in the series of videos connecting Newton's second law to the kinematic equations from the previous chapter, and a reminder, this is all in one dimension. So later on in this chapter we're going to extend all of this physics to 2 dimensions. And so I have 73 newtons for F1, 85 newtons for F2. The mass of the block is 6.8 kilograms. So again, we're sticking with units in the SI system, so we have nothing to convert to make our units consistent. So unit consistency is a running theme that is going to crop up over and over in this class. So 85 newtons minus 73 newtons is equal to 6.8 kilograms, applying Newton's second law. And we're going to find the acceleration. So the acceleration in this case is going to be 1.76 meter per second squared, and it's accelerating to the right. So this is sort of an intermediate result, not our final result. Alright, and I have distance. So I'm going to highlight in yellow what I have. So I have distance. Distance appears here and here. And I do have acceleration now. So I have acceleration, 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 and looking for time. So since I'm looking for time, this equation is eliminated right off the bat because it doesn't involve time at all. And let's see, then the block's initial velocity is 7.2, so I have initial velocity. So I have initial velocity, and initial velocity. Alright, so the problem with the bottom equation is that there are 2 unknowns, and that's too many, so that doesn't work. The top equation has 2 unknowns, and that's too many. Okay, so the second equation is just right because we have 1 unknown, time, and that's ideal. You have 1 equation, 1 unknown, then you're in good shape. Alright, so plugging in 340 meters for distance equals 7.2, and again I'm assuming that's to the right because it is positive, times time, plus 1/2 times 1.76. Usually by now I've dropped the units in the interest of clarity, because one of the first things young people have trouble with is distinguishing between the variables and the units, and sometimes they just all run together and all they see is a bunch of letters. So t squared. I've also dropped the delta because of it's not really important. Okay, so 7.2t plus, and I'm going to go ahead and take half of 1.76. I get 0.88. Alright, so I have a quadratic which needs to be put into descending order on one side with everything on one side, 0 on the other side. So if you recall from the last chapter, this enables us to identify the A coefficient, the B coefficient, the C coefficient that we're going to use in our quadratic formula to solve for time. So time in this case is going to be negative 7.2 plus or minus the square root of 7.2 squared minus 4 times 0.88 times negative 340, and so the 2 negatives cancel. 2a is 1.76. Alright, so these 2 negatives cancel, leaving me with certain to have a positive discriminant. which is helpful unless I want to get a complex time. So negative 7.2 plus or minus, and then evaluating the discriminant and taking the square root, I get 35.4. All of it divided by 1.76. Alright, so I'm not going to bother with the negative part because that's going to give me a negative time. I'm going to evaluate only the positive part. And I get 16.0. And since my units were consistent from the beginning, I know my time is going to come out in seconds. And that's the reason why you do a unit analysis, and you understand that newtons and kilograms and meters and seconds and so on all work together to give you the same result over and over. That's unit consistency. So it's going to take 16 seconds for this object to be displaced with those two forces acting on it for this particular amount of time, 16 seconds. It's going to displace this far, having had an initial velocity of 7.2 meters per second.